Today we're talking about the second invention necessary for the Nagasaki bomb to work. And that was a means of bringing a critical mass of plutonium together fast enough that it will not fizzle. The first mention of the possibility of an atomic bomb in the documents of the Manhattan Project is the so-called Frisch-Pearls Memorandum, which was received from England in 1941. Frisch and Pearls were two German scientists, German Jewish scientists, who left Germany at the time of the Hitler takeover of the educational system in Germany. They were working on nuclear energy because at the time it was not considered to be a strategic topic. As enemy aliens in Britain, they were not allowed to work on strategic topics. But they concluded that an atomic bomb was possible. They did this partly from erroneous information. They underestimated the critical mass by a factor of about 30. But they did conclude that an atomic bomb was possible, and their suggestion was to separate the critical mass and then bring the separate masses together using springs, having them spring-loaded with a trigger that released the spring and brought the halves of the critical mass together at the time of the nuclear explosion. The second set of serious discussions of the ways of bringing the parts of a critical mass together was a conference held in 1941 at Berkeley by Robert Oppenheimer and his research group, including a man named Robert Serber. They concluded by coming up with this diagram of a series of possible ways of bringing the critical mass together. I think you can see that the third one down is a variety of implosion, bringing the separate pieces of the critical mass together under the influence of high explosives, propelling them toward each other. This is not exactly the way it was done in the Manhattan Project, but the idea is the germ of what was done. The first possibility that was worked on actively by the Manhattan Project once Los Alamos was founded was the gun bomb. We've talked about the uranium gun bomb in the context of Little Boy, the bomb dropped on Hiroshima. And they thought that they could use a gun bomb for plutonium as well. It would have to be a higher velocity gun bomb. Little Boy's gun was about 1,000 feet per second, and the one they were contemplating for the plutonium bomb was going to be 3,000 feet per second, which is approximately the muzzle velocity of a tank gun. Here are some pictures of 3,000 feet per second guns that were contemplated for the plutonium bomb. When the actual plutonium started to show up, first from Oak Ridge in small quantities and then from Hanford in workable quantities, it turned out that it was contaminated with a little bit too much plutonium-240. We talked last time about how plutonium-239 is made in a nuclear reactor. What we didn't mention is that if you leave the plutonium-239 in there too long, it will soak up another neutron and become plutonium-240, which has an excessively high rate of spontaneous fission and therefore of generation of neutrons within the metal itself, which is something that has to be dealt with in order to prevent fizzles, premature detonations of an incomplete critical mass. A man named Seth Nettermeyer had been working on the possibility of implosion during the time that everyone else was working on the gun bomb. Unfortunately, in the year that he worked on this topic, he essentially got nowhere. So when it became clear that implosion was going to have to be the way that the plutonium bomb was initiated, it became necessary to stir things up at Los Alamos. Seth Nettermeyer was out, and this man, George Kistiakowsky, was in. George Kistiakowsky is a very interesting man. He started out life in Ukraine, where he was a Cossack. Cossacks are well known as the Tsar's shock troops, the Tsar's mounted cavalry. And when it came to spreading the Russian Revolution into Ukraine from the major cities of the USSR, the Cossacks fought back. They were members of the so-called White Russian Army. The Red Army was sent to conquer them. The Russian Revolution of 1917 was really just a revolution in a few major cities of that vast country. And it took a 5-year civil war to spread communism to all of the parts of the USSR. When the Red Army finally did defeat the White Army, Kistiakowsky had to leave Russia in a hurry. He went to Berlin, where he studied at the University of Berlin. He studied chemistry. And later on, he emigrated to the United States, where he was initially an instructor at Princeton. A few years later, he became a faculty member at Harvard University, and it was from Harvard that he was recruited to Los Alamos. I want to say a little bit about chemical explosives. These are the explosives that are used to compress the plutonium and bring on the nuclear explosion. The standard chemical explosive at the time, and even today, is called TNT, or trinitrotoluene. This is its structure. It's not the best possible explosive. If you count up the carbon atoms in this molecule, you'll see there are 7 of them, and only 6 oxygen atoms. The best explosive is one where all of the atoms in the explosive can wind up as gases and contribute to the expansion of the gases that constitutes the explosion. Here we don't have enough oxygens to turn all the carbons into carbon dioxide or even carbon monoxide. So, although it is not the most powerful explosive, TNT was very popular with the military because it's hard to ignite it. That means it's safe. Even if somebody fires a gun into it, it's probably not going to go off unless you actually use a detonator to set it off. A better explosive is this one, called RDX, for Research Department Explosive. You can see in this one there are only 3 carbons and a whole lot of extra oxygens and nitrogens. You can turn all 3 of those into CO2 and turn everything in this molecule into a gas, which is what you want in a good explosive. The other one I'm going to show you is called PETN, pentaerythritol tetranitrate. In this case, you have 5 carbon atoms and 12 oxygens. So again, this is an explosive that will change completely into gases. It's not quite as popular as the others because it's more sensitive. It's easier to set it off. So it's used in the Manhattan Project in the detonators that set off the other less sensitive explosives. Now, let's talk about what these things actually do. At the center of the plutonium bomb is a so-called pit of plutonium. It's exactly this size, 4 inches across. There's a 1-inch hole in the center. We'll talk next time about what that's for. Under the influence of the explosive surrounding it, this 4-inch sphere is converted to a tennis ball size. At this point, it is a liquid, a very highly compressed liquid, and this is the point where you want to set off the nuclear explosion in it. Now, the way that this is all done is with a soccer ball shaped collection of explosives. You can see 2 different kinds of polygons on the surface of the soccer ball. There are 12 pentagons and 20 hexagons, 32 polygons in all. And in the case of the bomb, these were all cast in high explosive. And you see the dots in the center of each of these polygons. Those represent the location of the detonators, right in the center of each one, with the intention that all of the detonators will go off at once. Now, if we look at this diagram of the plutonium bomb, you will see on the far left the yellow object is a detonator, and it is setting off the first brown-colored explosive, which is called composition B. It's a mixture of TNT and RDX. The speed of detonation in this material is about 8,000 meters per second. It goes really fast. And then it hits the tan material, which is the so-called explosive lens. This is made of baritol. Baritol is a mixture of TNT and barium nitrate, and the speed of detonation in baritol is only about 5,000 meters per second. So, if you calculate the shape of this explosive lens precisely, and this is the man who helped with that calculation, his name is John von Neumann. He was a Hungarian mathematician who had an important role in the Manhattan Project, and who also did some other very interesting things in his life, including he and Turing are the 2 people attributed with the way that computers are programmed today, stored program computers. And he also invented something called game theory, which is used in economics and in military planning. Now, the way that this works is that as the detonation wave passes through the explosive lens, it is made perfectly spherical. And then it goes through a second layer of composition B. Then it hits a large sphere made of aluminum, which is to transfer the energy of the explosion to the plutonium inside. After the aluminum, there's another layer of uranium. This is depleted uranium surrounding the plutonium, and in the very center of the plutonium is the initiator of the nuclear explosion, which we'll talk about next time.